You reach for a metal door handle, and a spark jumps to your fingertips. If we zoom in past the light of that flash, the reality of what just happened looks very different. In a fraction of a second, enough voltage bridged that gap to briefly tear apart the air molecules between your hand and the metal, transferring a massive amount of energy. To our eyes, this electrical discharge looks like a fluid, a sudden, continuous river of energy flowing from one surface to another. But that smooth flow is an illusion of scale. At the atomic level, the river disappears. Charge is actually a highly discrete, granular property. It exists strictly as countable individual units bound to the structure of matter. To accurately calculate the massive electrostatic forces that govern our physical world, we have to completely abandon our macroscopic intuition. We must map the behavior of these invisible, separate pieces from the ground up. Doing that requires a rigorous mathematical model built on absolute physical axioms. First, we have to isolate and define the absolute smallest discrete unit of charge that can exist in nature. Second, we must map the strict spatial relationship, the exact vector push and pull, between exactly two of these isolated charges in a vacuum. Finally, we need a mathematical rule that allows us to scale those two-body interactions up to handle complex multi-body systems. By defining the geometric and algebraic rules of subatomic particles, we can perfectly predict the chaotic macroscopic electrostatic forces that occur on our scale. We start with the absolute floor of electrical charge. In physics, this indivisible unit is universally denoted by the letter E. This immediately establishes the fundamental principle of quantization. All free charges in the universe are strictly integral multiples of this basic unit. We formulate this algebraically as Q equals n times E. The variable n represents any integer, positive or negative. You can have 1 unit of charge or -5 units. Because the math strictly forbids fractional charges, charge simply does not exist in continuous measurements. The standard SI unit for measuring charge is the coulomb. In this system, the exact microscopic value of E is 1.602 times 10 to the -19th coulombs. This step size is extremely small relative to our everyday experience. This is why macroscopic charge feels like a continuous flow. The gaps between these individual units are too fine for our senses to resolve. If you want to accumulate just 1 negative coulomb of charge, you have to divide 1 by that tiny value. It requires roughly 6.25 quintillion individual electrons. Because these quanta are discrete physical entities, they are bound by the law of conservation of charge. Within an isolated system, particles might repel each other or transfer between bodies, but the total algebraic sum of all those separate charges remains perfectly constant. Charge is a strictly quantized and indestructible currency. It only transfers between ledgers. It is never created or destroyed. Now that we have our discrete units, we calculate the mechanical force between exactly 2 of these isolated point charges suspended in a vacuum. We define their absolute spatial locations using position vectors, labeled R1 and R2. From those coordinates, we calculate the displacement vector. This measures the exact distance and straight line direction between the two entities. We call this R21. To lock down the orientation, we extract the unit vector. This acts as a pure, dimensionless directional indicator, pointing from Q1 to Q2. This gives us the components to build Coulomb's law. The magnitude of the force scales proportionally with the product of the two charge magnitudes, and it drops off strictly based on the square of the distance between them. When we combine that scalar magnitude with our unit vector, we get the final exact force vector exerted on charge 2 by charge 1. The algebra dictates the physical outcome. If both charges share the same sign, their product is positive. The math forces the resulting vector to push forward along the unit vector. That is repulsion. If the charges have opposite signs, their algebraic product becomes negative. The math flips the vector exactly 180 degrees inward. That is attraction. We can shift our perspective and calculate the counterforce exerted back on the first charge due to the second charge. Swapping the numerical indices in the equation produces a vector that is perfectly equal in magnitude but opposite in orientation. Through this vector formalism, electrostatic interactions flawlessly obey Newton's third law of action and reaction. This defines the two-body problem. But how do force calculations behave when a third point charge enters the system? Does this new particle disrupt, block, or alter the relationship already established between the first two? It does not. This is the principle of superposition. Pairwise electrostatic interactions are completely blind to the presence of surrounding charges. The original two-body force vector remains entirely unchanged by the new arrival. To find the true total force exerted on the target charge in this environment, we calculate the individual vectors for each interaction separately. Then we perform a linear vector addition, mapping them geometrically to find the single resulting force. Any complex electrostatic system, no matter how crowded it gets, is simply the linear geometric sum of isolated, undisturbed pairwise interactions. We can scale this mathematical model up drastically, taking it from 3 simple charges to a highly chaotic macrostatic system. Theoretically, the principle of superposition holds perfect mathematical integrity for any number of particles, but practically, attempting to track 10 to the 23rd individual vector sums is computationally impossible for everyday objects. Directly calculating discrete pairwise forces reaches its limit. We have to map the aggregate distortion of space itself. To understand continuous macroscopic systems, we must move past tracking individual point charges and instead map a continuous distribution across space, the electric field.